I think we can start like by welcoming everyone that is present here today. Thank you all for coming. I hope that this is a pleasant session with a lot of learning for all of you here today. This is once again another session of our Fiber Future Talks. And today our main topic will be on the innovations in sustainable fiber cultivation and its extraction. Today with us we have Percy.
Hello.
Good morning to you, Percy. I I seem to have lost your presentation.
Yeah, I can just begin if you want. And
No, I wanted to present to you, but I seem to have lost your bio that I was going to share. But Percy it's over here. No, well, Percy is a postdoc research fellow from the Swedish University of Agricultural Services. Um, he's doing a lot of research focused mostly on sustainability and circular economy, emphasizing on lignocellulosic composites and natural fiber characterization and utilization. Today, he'll be speaking to us on the hemp biomass valorization and on how properties, how the on the properties of fines for insulation and enhanced tensile strength of fiber non-wovens with MFC. So sorry for this kind of mess up. I was messing up some of the windows here. But Percy, feel free just to share your presentation. We are eager to know more on this subject from you. Thank you.
yeah, thanks, Pedro. Uh, let's get this going. Just gonna put up my presentation. While the other participants. So I think you will stop sharing, and then I will be able to share.
Yes,
Yeah,
stop share.
awesome. Okay, let's do this way. Um, I try this way. I hope it works.
Yeah, it is sharing now.
Awesome. All right, great. Thank you for having me here. I think Pedro kept he wanted us to present something in FIPSEN, basically to give an idea of what we're doing in this project with regards to extraction of fibers and biomass in general and application and the properties of the biomass. So today, as he already introduced me, my name is Percy, postdoc researcher at Swedish University of Agriculture in Sweden. So today I will talk a bit about hemp biomass, and the focus will be on the properties of fines in relation to insulation application and enhancing the properties of non-woven. So in reality, what we mean is that we have different aspects of hemp biomass. We have the fibers, and then we have the fines. So just to give a little bit of background, uh, the whole idea is to use renewable material. It's the focus for circular economy, for sustainability, and so on. But we also identify that when we talk about sustainability, there's a lot of emphasis on that, and it could also have some kind of implication in terms of resource utilization. And we notice, especially when we think about the common material, when we talk of lignocellulosic material in this regard, we talk about trees or the biomaterials. We see that there is a lot of there is more resource use, and this is actually in linearity with the increasing population demand and so on. So the goal is, of course, we need to be able to decouple to find new ways to sort of like increase or find new applications, find new biomass that we could use to also achieve the goals and results. So in this case, when we talk about hemp, it's one of those natural fibers, and one of those natural fibers or biomass that is already identified as a possibility to sort of help decouple these economic activities from excessive natural resource consumption. And in this case, we know fibers in general is something that is already well, say, used, currently gaining more application, especially in the automotive industry. But another aspect to fiber is that it comes from stock, and more often than not, when the stocks are processed, you have different fractions of material. So in this case, we have the technical fibers, which is commonly what is applied in automotive industry, which accounts for about 25% of hemp stock. And then we have fines that are also generated during the process. So this brings up the whole goal for FibCen. So in terms of FibCen, in aligning with this basic, economic expansion issue and to sort of like decouple, FibCen has a concept which is more or less to boost the rural economy and competitiveness for primary production and industry, and of course to use underexploited raw materials. In this case, we talk about hemp biomass. So how, first, just to understand how the fines, how the fibers are produced, a typical process. We usually take the straw, and in this case, one of our partners in Germany, BAFA, actually does this activity, planting the seeds, harvesting the fibers, processing the fibers, or processing the stalk into fibers, and the process leads to generation of fines and other fractions. So yeah, just give a brief idea how this is done. The straw is fed into a certain mechanical decorticator, but in this case, there are other fractions that are generated, and these fractions are often cleaned, separated from each other just to get like a better output. Fibers are separated from fines, fines are separated from chives, and of course, we are able to collect the different fractions of hemp stock. So to kind of like now bring the main focus to our topic today, I will focus this presentation from three aspects. So the first one will be to sort of like give some background information, DNA of the hemp fiber, specifically the fiber we're using, to give some information on how we sort of like improve non-wovens from these hemp fibers, which are the long fibers. And then the second aspect will be to talk about the properties of the fines and how we incorporate these fines into making non-woven thermal insulation panels, and of course the performance of these thermal insulation panels. So to begin with, we look at the properties of hemp's long technical fibers. And from our perspective, this is where SLU, the Swedish university, comes in. We characterize the fibers. So we have partners who are sort of like, buffer plants and source the biomass, process the biomass into the different fractions. Our own goal is to understand the properties of the biomass. And of course, because when it comes to bio-based materials in general, in the form of material science, the properties of the material always more often than not defines the property of the final product. And so here we just give like just a basic understanding what is the chemical composition of our fibers. And of course, this we did with a method called the Valencony protocol. And this protocol, of course, helps us to understand what is the composition of soluble content, hemicelluloses, celluloses, lignin, and residual ash. And the main goal here is that this composition influences the properties of the fibers and how the fibers will behave in application. So we found that the results are not so different from what we already know from literature. Of course, the lignin content in these fibers were pretty high, but also in literature, we found some results with up to 13% lignin content. So to also understand what is the base property of the fiber before they are also applied in non-woven, we did what we call this tensile mechanical test. And for that, we have used the fibers that are about 30 millimeters, 3 centimeters. And again, we were able to find out what is the range of performance for our fiber. And we found that the tensile strength is within the middle range. However, modulus is at lower range of what is published in literature. And you'll see that there is commonly a huge variation in terms of strength and modulus, and this is due to the fact that it's not as easy to obtain individual or single fibers, and more often than not, as you'd see also in the variation in diameters of the fibers, these are also influencing the properties of the fibers in general. So after we examined these base properties of our fibers, then we applied the fibers in non-woven. And this is an activity that was done by another partner called Comatex. And what they've done here is to produce some batch of non-woven material, and with a target area weight of 300 grams per square meter. In this case, we will talk about 3 batch of this non-woven. In 2 batch, they have like used the same binder, but different loading. So in the first case, what I referred to as round 2 is non-woven with about 15% binder. In this case, we were able to achieve the target area weight. In the second case, you have a binder with non-woven with 5% binder amount, a slight decrease in target in achieving our target. And in the third case, we've used epoxy resin, and this is a bit different resin because compared to the PPPE bicomponent fiber, because in this case of bicomponent fiber, as the final point suggests, fiber is in the form of the fiber, which is also in the form of the we have our hemp fibers, then we use a binder which is also in a fibrous form. In the case of epoxy resin, we use epoxy powder. So and the process is more or less hair laid, which is more like a dry process for forming non-woven material. So yeah, we see that their results show some variation in terms of if low wetting is achieved with using low loading content in the case of the bicomponent binder, but also due to the use of the powder resin in combination with the hemp fiber, we see also a slight, deviation from achieving the target area weight. So again, we get the non-wovens from Comatex, and our goal is also to sort of like define the DNA of the non-woven. So we do what? We just measure the tensile properties of this non-woven. And in any case, we could see the variation in terms of first the binder type, that with the epoxy resin, the strength properties are pretty low, which is perhaps understandable when you use a powder in combination with fiber. However, in the case of PP, we see also like increasing the loading, which is normally the case, increase the tensile properties of the nonwoven. So about 2 times increase with in tensile properties with 3 times increase in loading. And what we did again is we realized that regardless of the fact that we already understand the area weight of the nonwoven as per what was delivered, due to the way this test was performed, it was imperative to sort of like understand what is the impact of the weight of the nonwoven on the tensile properties. So the reason being, we noticed variation across the nonwoven rolls in terms of the area weight. So we wanted to also normalize the tensile properties. So from the base nonwoven material, we could see that while there are variation, it's not anything notable from the variation in the area weight of the nonwovens. So just to give a brief summary from this perspective is that the whole goal of this nonwoven is this nonwoven should be applied again in hybrid composite material. We define the properties of the nonwoven, and ultimately we see some, variation in tensile properties or mechanical performance. But this is just the base to define the DNA of the material, and it doesn't really say it's a bad material or it's not going to function. So the next point of reference for us will be to check how these nonwovens will behave, how we will the ability for us to incorporate MFC, because what we achieve with 5% PP binder could be better if it works with MFC in improving the mechanical properties, and we're able to increase these mechanical properties. Or in the case of epoxy, just to give like a little bit of information that we already got the feedback from the hybrid composite manufacturers or project partner that they prefer to work with the epoxy resin. So regardless of the fact that we saw a decrease in properties. So moving forward, we incorporated MFC into the nonwovens. And to do this, we also work together with another partner called Fiberline, based in the UK, and they supplied us with MFC. And the crucial part for us here is the emulsion nature of MFC, which makes it quite tedious in combining with the nonwoven. Nonwovens are typically bulky. MFC have very low solids content, but you'll see the emulsion effect makes it a bit less, easy to kind of like combine with nonwoven. So we examined the incorporation of MFC at the lab scale, and for us to do that, the goal for the entire, say, MFC incorporation is to be able to spray MFC along the line in the industry onto the nonwovens. But in the lab, what we did was we had to pre-dilute the MFC to sort of like enable adequate coverage across the nonwoven. And of course, it means we needed to introduce again water. So looking back at the batch of MFC of nonwoven we've worked with, again, the 3 rounds of nonwoven, we then tested retention rates, target retention rates of 1%, 2%, and 3%. So in this case, again, we incorporated these nonwovens with MFC by spraying after dilution with based on the mass of the nonwoven to have a solution target of 1:7, which is 1 gram to 7 gram of solution. And then again, we examine the tensile properties of this nonwoven. So just to be transparent and to give some kind of clarity, complexities arise just in this process of introducing water. First, you have nonwovens that are already with binder. Introducing water, drying, this post-treatment effect made it slightly difficult to be able to actually estimate the retention of MFC. So when we estimated MFC via the controls without MFC, when we investigated the MFC in these non-wovens just by spraying with water to kind of like give the same, to give the same effect as to the non-woven as to later when we examine the properties, we already realized that there is already a difference in the weight before and after. Either in one case it's lower, in another case it's higher. So there are some issues in that regard. This was particularly prominent with the epoxy resin, which is the powdered binder. And what we realized is that the possibility for leaching, for removal of non-binded epoxy and whatnot. So these are aspects we feel made it a bit difficult to sort of like define the retention rate as per the target. So in any case, the result how we present will be with regards to target MFC retention rather than actual MFC retention. So to check, because in our case, we could say for sure we see visibly that after spraying there is MFC on non-wovens, but scientifically we needed to also be able to prove that, and we corroborate this with FTIR analysis first by understanding the structural properties of the MFC, and for this we see that we see the common typical bands which are more typical for cellulose material. But in any case, we see some differences when you will think about the lignocellulosic material. For instance, we have included here fiber FTIR, and we can see a clear difference between fiber FTIR and let's find my pointer, between fiber FTIR at the 1650 range and with MFC. So what we did here was we paid more attention to this, say, region, which is more or less indication of epoxy presence, because here you have the fiber, and with the non-woven, we have these bands which are introduced with epoxy. And then we pay again attention to this part and to this part, which are more defined with incorporation of MFC. So we noticed that the definition of those regions increased with MFC incorporation. So regardless of the fact that in some retention case, we saw like when we measured with 3% retention, it probably showed lower MFC retention, but the actual, but this doesn't give like an actual picture or the true picture. We, while not directly visible from these two, it's also what we notice is when we sort of like line together the round 2 and round 4 non-wovens, we saw that there was a difference already in terms of the intensity of the peaks that are more like aligned with the PPPE binder, which is typically due to the lower, incorporation rate. And in the case of round 5, which is more different, slightly different binder, you see that we don't see this typical PPPE peak, but we see that here in this region for epoxy. So when we move forward and then we now measure the tensor properties after MFC incorporation, we start with round 4, and what we see already is that this is the base control which are previously introduced. The tensor properties of the base control, the tensor properties of the MFC incorporated target retention 1%, and we see that already there is a substantial increase in these properties of the MFC of the non-woven with this MFC incorporation. From this result, what we notice is that at 2% retention, we already have some kind of optimum performance for this MFC. With 3% retention, we don't see any linearity in increase in terms of performance, especially when we normalize the result with the weight of the nonwovens. So to bring back the issue with complexity of understanding retention, we try to sort of like control every aspect of our treatment and to sort of like eliminate any factors for error. And in this case, we have measured the individual strips, the weight of the individual strips that were used, and then we try to corroborate or try to correlate this weight to the say performance of these strips. And in the case where we saw, like when we measured target retention was 2%, 2.6% with 1% incorporation of MFC, that when we look at the base say properties, that we see that there is no real implication that this MFC retention is lower for this non-woven, especially when we normalize with the weight of the strips. So this also further sort of like corroborates our point that the true value of MFC retention is not measurable by just mass change. So when we check the run 2, which is more or less the run with the higher epoxy, bicomponent binder, PE, we see that compared to run 4, we already have increase in terms of control, as I already previously indicated. But in the case of run 2, we see, of course, that there's an increase, which is with the 1% incorporation, and this was substantial. We found this that this increase with 1% incorporation was quite substantial, at least compared to the control. But in the case again with 2% and 3% MFC incorporation, we didn't see any real increase. So with the run 2, we found that while the initial non-woven has a very high performance, often due to the adequate wefting, which means adequate coverage of the fibers with the bicomponent binder, this coverage, it becomes more like a limitation for penetration of MFC into the core of the non-woven. So via just visual observation, what we notice is that majority of the spraying MFC remain on the surface of the non-woven, compared to in the case of run 4, where MFC is able to penetrate beyond the surface of the non-woven. So in this case, the result you see here just comes from the implication of MFC on the surface of the non-woven. And then in the case of run 2, as we previously saw, that the base performance was the lowest, which was at 40 Newton per meter. But we see again that in any case that implication with 1% retention, notable increase. With 2% in retention, this is almost 12 times increase compared to the base control. So this for us is very crucial, because we see that despite the fact that we have very low performance compared to, say, PPPE binder, that we are able to actually get towards the other binder type by incorporating MFC. And MFC works better with epoxy binder compared to PPPE. And this is also good in this regard, because the other partner identifies this particular batch of non-woven to be the best for them to incorporate into the hybrid composite. So if we're able to move forward with this kind of result, then it means that every aspect of the hybrid composite aligns, and we are able to actually find a very the optimum parameters, incorporation, and materials for the final product. So just to buttress again the point with regards to issues with MFC incorporation, I bring forward again what we noticed, like the main reason why we feel that this retention is also not justifiable by just simply measuring the weight before and after. Here we find the technical fiber itself before the use of technical fiber in nonwoven. And in this case, we see when we introduce the binder, we have a peak, which is synonymous with epoxy. In this case, with dilution with water, we see that this peak is basically attenuated. And so we say for sure that it's an effect of non-binded epoxy resin in the non-woven. So just to give a brief summary of this first aspect of the work, that we are able to successfully incorporate MFC on nonwovens. We see the results clearly, and we believe that run 5 could be significantly used with 2% incorporation. Of course, 2% also would work for the other batch of bicomponent binder. So I don't know if you have any questions at this stage before I move to the next point.
I think everybody's shy, Percy.
Okay, all right. Maybe some questions later. Please just feel free.
Yeah.
So
and even and even if you are shy and don't want to turn up your mics, you can just leave the message on the chat, and we can just read it out for Percy.
Awesome. Okay, so in the next aspect, we look at the properties and performance of fines. So this for me, I mean, MFC incorporation and all that is quite interesting. I like it, but I like this aspect better or more because we look at fines when we talk about hemp stalk as negligible, as a material commonly just discarded. So more often than not, there is a lot of emphasis on chives. And there's chives are found application in hempcrete and some other type of boards. And fiber is where everyone pays a lot of attention, hemp fibers. But what happens to the fines? And when we talk about the fines, I already gave like before defined the fines as constituting 2 to 4% of the stock when it's processed. In this particular work, the batch of stock obtainable in in an hectare of land is about 8 kilograms of hemp straw. And this is basically from 1 kilogram of hemp seed. And what it implies is that 480 kilograms of fines are obtained as fractions from processing the stock. And this is where the goal of FIPSing comes in again, how to use this fines. So these fines need to find use, because otherwise then it's we don't achieve the whole point of circularity and whatnot. So for this particular aspect, what we've done is we already have a partner, Suprema, that is working with wood fibers in insulation products. And what Suprema now, well, the whole concept was to kind of like incorporate fines as a substitution, partly for wood or as a total substitute. And again, we worked here with the bicomponent fiber, the PE. And in this case, I will introduce some of the panels, what we've worked with. First, we look at the wood reference, which is the panel from the 100% incorporation of wood. Of course, this is important so we can compare our results. And then we also investigated the 3 batch of which is 25% incorporation of hemp short fibers, 50% incorporation, up to 100%. The same thing for the super short fibers. These 2 batch of material I previously introduced. And in this case, we have a target of 40 millimeter thickness and 55 kilogram density. So this is basically a flexible insulation panel. But of course, we initially examined, this is also the goal. The goal was to examine all this incorporation rate. But what we noticed is that with the very, very short fibers, it was impossible for us to achieve the set goals of 40 millimeters with 5 kilogram per cubic meter. And I will tell you why later. So here we have the schematic, the process, what they've employed in making this product. Of course, first comes the mixing stage where the fines and the binders are mixed together. Then this material is blown into another stage. From this stage, the mixing is further consolidated, and then the material moved into a cooker. So before pressing, the material is allowed to cook for a certain period of time before the material is pressed at around 140 degrees Celsius. So I just give a brief idea of the nature of the panel with 100% wood or 100% short fibers, and this is the 100% super short fibers. Again, when we talk about the material as our own interest in SLU to characterize the input material, understand the properties of this material, and how this material will, influence the final properties of the product. So the first point of call for us was to actually define the particle size, so the fiber length of these fines, of what we call the fines, and to compare these fiber lengths to that of the reference wood. And we did this using the Cupic, which is a device that enables us to feed in these fines. It has different feeder rates, but different feeders. But for this particular test, we use the dry dispersion unit, Rodox. And what we find, just looking at this image here, is that with the super short, which I call SKF, you see that the median fiber length is the shortest. When we look at the median fiber length in terms of the short fibers, it's almost about the same as the reference wood. Of course, when we look at aside the median, the reference wood still has longer fibers. And the goal for us is to see how this fiber length will, play an influence in this final product. And which brings us back to the point of not achieving the target thickness and target density. And this is one of the reasons why we could not achieve that for SKF, because the fibers are too short. And for that, it would require a different approach or increasing target density or whatnot. But of course, this means that you have a product with a higher density compared to the base-like material you're trying to substitute. Then the next goal for us was to understand the physical properties of the material, because if the material is supposedly a thermal insulation product, it's also important to know how this material behaves in nature. These properties are often influenced, of course, by the chemical composition of the material as well. And so we, of course, measure the sorption properties, and we compare that to the base wood material. And what we noticed from sorption properties is that the super short fibers have a high rate of sorption. This I will just highlight with this equation here. So the higher numbers, the higher this number, the higher the gradient. So you see that in terms of sorption rate, that actually KF has a lower sorption rate compared to the wood reference, while SKF has a higher sorption rate compared to the wood reference. So What we did then is to understand why, more often than not, chemical composition again plays an impact in terms of these kind of properties. And so we found that with SKF, which is a super short hemp fibers that substantially high soluble content, high variation in lignin content, and this is because the material comes more from the core, which is always the lignin-rich section of the stalk. And in comparison to reference, we see that this low absorption rate for reference for the KF has implication with the hemicellulose content, because wood in general, of course, when we talk about hemicelluloses for wood and for hemp, it's not directly comparable in terms of specific type of sealants in this lignocellulosic material. However, we still see that in the case of wood, the high hemicellulose content could have played the implication in why the absorption rate is slightly higher compared to KF. So furthermore, we then examine this chemical structure and composition with thermographic and gravimetric analysis. And this gives us an idea of the thermal stability of the material. And we see correlation between what we already observed in terms of chemical composition and with a reference. Obviously, what we see with reference is that lower cellulose content. However, we see that, for instance, at the 50% mass loss, which is often associated with about 50% of the material incorporating cellulose thermally degraded, that wood, actually, this wood reference has better thermal stability compared to the hemp biomass. So you could ask why that is. If cellulose has this kind of high degradation, thermal degradation, but we noticed as well that wood had quite a high substantial amount of lignin, which has often the high variation in thermal decomposition. But when you talk about the thermal stability of a lignocellulosic material, it's not just only about the chemical composition, but it's about the structure in itself. So in the case of wood and what we call the relationship between lignin and hemicelluloses as against celluloses, there is a more protective factor compared to hemp shies or to hemp biomass. So this is why, in any case, we see much better thermal stability for the reference wood compared to the hemp. But while we notice that in the case of the SKF and KF, with the super short and short fibers, there are like variations in these slight variations in thermal stability, but this where it wasn't anything notable. The only notable change or increase in terms of thermal stability was achieved with the 50% mass loss. So, which again shows that KF is slightly more thermally stable than SKF, which corroborates the chemical composition of the material. This also translates to the, it also translates to the chemical and structural composition. And we see that while we identify this crystallinity index, size of the crystals, and the main reason is because when we talk about thermal conductivity, this plays a crucial factor. So why? The higher the crystallinity index, the more likely the material is more thermally conductive, especially in the case of, as we see with the SKF and KF. So what it tells is that there is a potential for the wood reference to perform better. But of course, we try to see what is this variation in performance as a whole. So without further ado, we look at the panel properties. And as I mentioned previously, that we decided not to move forward with the super short fibers, the very short fibers. And we noticed in general the high dust content in the very short fibers from the panel. And this is, of course, due to the short fiber length, of the fibers, but also the inability of these fibers to achieve the target thickness. Then we also investigated the tensile properties, in this case, perpendicular to the surface of the boards. And of course, we see that the wood tensile properties are quite higher compared to the hemp biomass. But of course, we relate these to first the interaction between the wood and the binder, and of course, the size of the wood fibers. And then we, try to understand what is the reaction to fire properties of the panel. And in this case, we see that in the case of all our products, first and foremost, also the same situation with this perpendicular, this tensile test, that even though there are variations, they all achieve the target, which is the 1 kilopascals that Suprema already has as a base target for this kind of product. In the case of reaction to fire properties, in looking at lignocellulosic material in general, without any fire retardant or treatment or whatnot, they will always, react with fire. So this is just a common knowledge. But the main point to look at is that there's already a class of say performance, and in this case we see that all the products pretty much achieve lower flame height to this class, but more imperatively, we see that with the short fibers, that this is the slightly longer fines, that there is even better, performance in this case. And yeah, the main point here is that this is the particular fiber with the lowest lignin content. And of course, when lignin can also play very high importance when it comes to the especially reaction to fire properties of lignocellulosic material. Then the main point, which is the thermal insulation and thermal conductivity, as we already saw, as I pointed out from the crystallinity index, that it's more likely wood will have the wood reference due to the low crystallinity index would be better in this regard, and we see that from the final product. What we see and notice is that with 100% incorporation, this is really there's a huge change in thermal conductivity. And in the case of 25%, 50%, we didn't see any real difference. And actually, for all the hemp biomass, they behaved about the same. So this is the thing. And what it tells us is that it's possible for us to incorporate these fines when we look at all the properties together. It's possible to incorporate these fines up to 50% incorporation rate in the panel. So it brings another question that perhaps there is a need to also examine the 80% incorporation rate if the 100% is not so good, but maybe 80% could also be something to look at. So this is what we're also currently working on, because the goal is, if you're able to, the optimum substitution is beneficial in this case. So so this is basically a good result for us. Of course, it still needs some work and also validation in the industry. So to summarize in general for this particular say section, that we did find variations across fractions of hemp stock, from fibers to fines and whatnot. Of course, shives also, which I know have been studied, also have some differences in properties. So we cannot totally substitute wood fibers with very short hemp fibers, especially when we look at all the results put together, primarily because the fiber lengths are too short and the dust content is higher in this regard. And while we see that the thermal insulation is high for the hemp panels, these values fall within the common range for insulation panels. So it means that this material, of course, why it's not as proficient as the wood fibers, it still falls within the range of materials of this product. And then overall, 50% incorporation would work for the short fibers. If we are able to sort of like optimize better performance and to sort of like find a suitable application, then 100% of short fibers could also be used, especially when we think about the fact that this fiber gave very good reaction to fire compared to wood reference. So the work continues in this regard for us in the industrial viability. And so I give the overall conclusion that the work just shows or shed light that it's important to sort of like understand that natural materials such as hemp could find varying application if this material is well, say, studied, sorted, and if each fractions are targeted. So which was the goal for us in this case. And the current results actually gives very good implication for the industry. And so that's the next goal for us, to provide our industrial partners with this data, which they would now verify going forward. So I just introduced our partners in this work, and I say thank you for your attention.
Thank you very much, Percy, for your presentation. I think it was very insightful. And without knowing, you almost now in the end present our next speakers that are from FCBA, which are also FIPSON partners, but we will leave that for later. So I would like to invite you, if someone has some questions for Percy that you want him to answer, please speak now.
I have a question to, I just, maybe I was late connected, so I'm sorry if I asked something which was maybe said before, regarding like the industrialization or the interest from industry regarding the hemp. So to get it interested to use actually the byproduct or biomass, and like quantity wise, would it be possible then in Europe to grow enough hemp to satisfy also, for example, this kind of technical applications from the hemp, from the short or middle fiber?
Yes, I don't know why I'm unable to share my video again of myself, but yeah, totally, because like I mentioned, our partner BAFA in Germany, they already produce these fibers for the automotive industry. So they have a field where they're able to, they have the seeds, and they produce about 8,000 kilograms of these fibers per hectare of land. So they already have, and I'm sure it's not only buffer. I understand this is a very interesting question, because more often than not, when we talk about sustainability, circularity, the source of raw material and the sustainable output of raw material is also critical. And more often than not, even here in Sweden, we've been approached by two, partners, hemp innovation just came to us and was like, oh, we have a lot of hemp and we don't know what to do with them. So it's something that is currently really growing, and it will only keep growing, with such information, with such data. So yeah, BAFA already has this going pretty well. And if we think about Germany, it's more like an automotive industry country. So they have partners that they produce these technical fibers for. Yeah.
Thank you for your answer, Percy. So if we don't have more questions now, let's just have a quick 5-minute break for everybody to get up, stretch their legs, have a coffee if you want to, and we'll get back here. Okay, let's do it 10 minutes. Let's meet here at 11, and we'll get back to it with Sandra and Arthur for them to present to us their presentation. Okay, so see you in a while. Thank you very much.
Okay. Thank you. See you.
Thank you, Pedro.
Here we are back again to continue our FibreFuture Talks session. Next, we will have Sandra and Arthur. Um, Sandra is a researcher and a project manager at the FCBA Institute of Technology, where she has been leading innovative work for over 18 years now. Her expertise spans over biochemistry, biotechnology, lignocellulose materials, wood-based products, and bio-based adhesives. She is one of the supervisors of Arthur Valencony's PhD thesis and brings extensive knowledge of lignocellulose materials and their transformation into high-performance sustainable products. Her work plays a key role in advancing bio-based innovation for sectors like packaging and construction. Welcome, Sandra, to our FibreFuture Talk session.
Thank you, Pedro, for your introduction.
And also we'll have Arthur Valencony. Arthur is a PhD student at the Grenoble INP, UGA, he's conducting his research now in collaboration with the FCBA as a part of the European Bio-LUSH project. His work is focusing on how to extract cellulose for underutilized biomass to create nanocelluloses and microfibrillated celluloses, the so-called MFCs that Percy also talked about before. With these applications in sectors like the automotive and food packaging. Through his research, he aims to contribute to the development of a greener bio-based materials that support a sustainable future. Welcome, Arthur.
Thank you, Pedro.
So the floor is yours. Feel free just to, I'll stop sharing so you can you can share your presentations and go ahead.
Can you see the presentation now?
Yes.
Yes? Okay. So I will start this presentation. Thank you, Pedro, for the introduction. We will make the presentation together, Arthur and me. And we present today in this webinar organized by Bio-LUSH and FibreFuture project, a general presentation about the wood and the wood fiber extraction and the different converting steps to produce high-quality fibers and nanocellulose. So just a small introduction about FCBA. Arthur and me are working in FCBA, which is a technical center dedicated for the wood sector. And based in France, we are 270 people in FCBA in different places. The main place is in close to Paris and work for furniture development. The second place is in Bordeaux, which work on building, and our lab is based in Grenoble in the intake fiber division. And we work on fiber and molecule extraction, byproduct from wood industrial valorization, industrial process simulation at pilot scale, and wood panels production. FCBA is a transsectorial technical center, which were dedicated for wood, and our activity sector is dedicated to forestry. So the wood studio and genetics, silviculture, logging, and supply chain. We work on primary and second transformation with a sawmill, for different application, energy, pulp and paper panel production, but for biomolecule extraction and plant chemistry. In terms of other dedicated sector, we work for building, construction sector, and furniture development, with different transversal application concerning global material, carbon footprint, and multi-sector health study. So today we have a presentation in 3 different parts, and we will first introduce the different fiber quality we can extract from plants. Now, Percy just before made a good presentation about what we have about hemp valorization. Here we will discuss for different plants, but have a specific focus about what will be done with wood fibers, and more precisely the production of chemical pulp produced from wood, the production of this chemical pulp is craft pulp from pulp and paper industry and other markets. And we will finally present a new valorization of this fiber into microfibrillated cellulose. But just to start, we have to have a focus on the different quality of fibers we can obtain. We have different sources of fibers we can use from annual plants. Our first are different straw, like wheat straw or rice straw or different nature of straw of cereals. And this straw has the particularity to have short fibers. Other family of plants, annual plants, can give long fibers, and that are particularly interesting for different applications when these extracted fibers can be used in numerous sectors. But this plant can be organized in different methods. For example, if we consider hemp or flax, stems are valorized stems of hemp, flax, or kenaf, for example. If we consider sisal or habaca, the leaf have fiber are directly valorized from the leaf. And another type of valorization is the case of the cotton, where here is a seed. Long fibers are extracted from seed. So we have different quality of plants with totally different quality of fibers at the end. The other type of extraction can be made from wood. From wood, we have 2 different family of wood. We can have the hardwood and softwood. From hardwood, the quality of the different type of wood give different quality of fibers. Hardwood are shorter than softwood, and we will see after this different type of fibers. So the extraction of fibers for these annual plants or wood are performed from different methods. If we consider the annual plants, the main treatment can be mechanical treatment, obtain a numerous fraction, different method of grinding or defibering, allow to obtain different fraction. We can obtain aggregates and fibers from different dimension, from millimeter, from decimeter. So we have a very important aspect ratio from these fibers and different composition too. If we consider here flax, we see that we can have different fraction. We can directly obtain very long fibers. We can allow to obtain non-woven and yarn. But we have different fraction with low quality fibers and chives. In this case, we can imagine different transformation to obtain other quality of materials in compounds, insulation material, or as additive in concrete, for example. Okay. If we focused on the composition and the structure on the fibers, we can have really different composition. From wood, we have here different quality of wood. First, softwood like spruce, pine, cedar, for example. Other are hardwood like birch, poplar, which is the most used to make pulp. We have different quality in terms of chemical composition, cellulose, hemicellulose, and lignin. Cellulose is always a higher content, and lignin, present in a lower quantity, is a second component present in this type of fibers. Depending the quantity of lignin and the nature of the lignin, fibers will be more or less well individualized by mechanical or chemical treatment. If we consider the annual plants, here are just some example with hemp and flax, we see that depending the type of fiber isolated, we can have really pure cellulosic material with low content of lignin and high content of cellulose. And the crystallinity of these material is really different, with really high crystallinity for annual plants than for wood one. If now we consider the production of fibers from wood, production is different that we can obtain with annual plants. Of course, we can consider that to obtain fiber from wood matrix, we can apply mechanical treatment. Mechanical treatment can be performed with refiner, with or without steam addition, with the objective to extract fibrous element more or less individualized. Depending the type of application, if for insulation, for example, is not a problem to have some ships with aggregates of different fiber together. From pulp use, individual fibers are more necessary. To obtain higher degradation, individualization of the fibers, this mechanical treatment can be combined with chemical treatment or enzymatic one. If we want to produce really well individualized fibers from wood, one solution is to use chemical treatment where the part of non-cellulosic fibers is dissolved. In this case, pulp cooking for paper application mainly are made from craft alkaline process or sulfite acidic process. In this case, the chemicals introduced, treatment are made with these chemicals and high temperature between 150 to 170 degrees approximately. This treatment allows a total lignin dissolution and to obtain individualized fibers. And in all the case, we can improve efficiency of the different separation, chemical or mechanical, by enzymatic treatment of fibers by bacteria, fungi, or enzyme. These different fibers can be after use in different for different application. Depending the type of fiber we obtain, we can imagine different applications. For example, for insulation, mainly mechanical treatment of fibers can be used. For furniture and panel, we can individualize fibers, which can be used after for MDF or HDF process. And in this case, we don't need to delinify the fibers and obtain good fibers quality with mechanical treatment. The same for composites. But if we want to use fibers for pulp or for textile application, the main fibers are produced by chemical treatment. For textile application, sometimes after obtained pulp, different treatment are performed to have cellulose regenerated cellulose obtained to make different textile yarn. If we consider the wood structure to obtain cellulose, we use directly the wood from tree. When we have either specific microstructure with big cells, with composite made from composite cells, made from different walls. In these different walls, cellulosic microfibers are organized with hemicellulose and lignin in the structure, and we have a composite structure with this microfibril of cellulose organized with hemicellulose and lignin, like concrete around the cellulosic materials. So if we want to isolate the microfibril, the microfibrils of cellulose, we need to destructure totally the wall of the cell of food. We can first obtain fibers, and from these fibers, we can isolate microfibrils bundles. To facilitate the isolation, we can have mechanical treatment, but if we remove the lignin present in the fibers, the insulation of microfibrillar elements will be easier to obtain. So all the pulp treatments are made to facilitate this insulation. So now I will let Arthur present you the valorization of pulp with the different methods.
Okay, thank you, Sandra, for this good introduction. So as explained, yeah, different ways to valorize the wood into pulp. So the first one is the mechanical one, but we obviously see the trend of this kind of pulp, which is decreasing because it produces less lower quality fibers for the kind of application that we're trying to develop today. In the middle, we have the semi-chemical processing that are used, but not as much. And the ones that in the trend are the chemical processes with the sulfite process and the craft process, which is the most conventional one. And this is the one that we will talk about, and with all the different steps of this process to produce a pulp, fiber pulp. So the craft process in general, so this process has been invented at the end of the 19th century in Germany, so it's quite an old and established process. And 10 years later, the first pulp mill has been opened in Sweden, which is one of the biggest pulp producer in Europe and even in the world. And it has been the craft process has been developed with the recovery boiler invention in the 30s, which improved the chemical recovery and helps to decrease the chemical consumption in these mills. So the objectives of the craft process is to separate the three components, as explained before, the cellulose and hemicelluloses on one side, that would be inside the pulp that we'll have. And on the other side, we have some black liquor that is precipitated to obtain lignin that can be useful for different many applications. Okay, so regarding the craft pulp mill, so we start from wood that have been separated, where we have separated the bark and the wood, the wood structure. In this wood, we have the three main components that are going into the craft pulp mill, and we can have on one side the cellulose and hemicellulose pulp that can be converted into a paper, for example, and on the other side, which is maybe the most complicated part of the craft pulp, is the black liquor that is precipitated and evaporated to recover lignin, and on the other side to recover the chemicals that we introduced before. So these chemicals are recovered into the green liquor, which is how do you say, which is improved to obtain again white liquor that is introduced again in the craft cooking. Okay, so different parameters in this craft process. So regarding first the process, the cooking profile is interesting to see with the temperature and time. And to do so, we can talk about the H factor, which is an interesting parameter. So the H factor is has been introduced by Vroom in 1957. It is based on average law, and it takes into account temperature and time to establish a control parameter for this cooking. So it represents the time expressed in hours of an equivalent cooking at 100 Celsius degrees. So with that, we can compare a fast cooking at high temperature, for example, with a longer cooking at lower temperature. Another interesting parameter is the wood, because as Sandra explained, we can have different type of wood. So, for example, hardwood or softwood, which are the main wood process into craft process. The ratio to liquor wood, meaning the quantity of wood for a quantity of liquor introduced, that will have an impact on the consumption of chemicals, for example, and the wood chip size. The wood chips are usually 3 to 5 centimeters square and around 5 millimeters thickness. But if you decrease the wood chip size, the chemicals can go easier in the wood chips, but you will consume more chemicals. So there is this size that needs to be controlled. And finally, the white liquor, meaning the chemicals introduced into the craft process. So for the craft process, it is an alkaline process with sodium hydroxide and Na2S introduced, which are the two main components of the white liquor. And obviously, you can also add water to control this ratio to liquor parameter. And we can see, for example, a cooking profile where we have control temperature increase with a plateau at a certain temperature, which can be, as Sandra said, for between 150 degrees to up to 170. And at the end, the wood chips, which have been converted, I would say, into pulp, are defibrillated, and the pulp is cleaned to eliminate the black liquor. So the craft cooking can have different effects on the biomass. I will not explain all the three different stages of the craft process, but we have three different delignification phases: the initial, the bulk, and the residual one. But the most interesting one is the bulk one, where we have the more lignin eliminated. And we can see on the right bottom images the different shape of the wood chips along the cooking, where we start from destructured wood chips to at the end pulp with individualized fibers. Okay. So following this craft process, we can also want to have more bleach fibers. So we will talk about the bleaching step, which will eliminate the chromophore compounds that are responsible of the pulp color. These chromophores have been created during the craft pulp, so we want to eliminate it in this bleaching step, and we also want to eliminate the residual lignin, which is that we still have into the craft pulp at around 2 to 5%. Different kind of bleaching can be found today with different compounds, with the oxidizing one and the reducing ones. The one which is the most used is the chlorine dioxide, but it contains chlorine, so it can be hazardous for the environment. This is why some totally chlorine-free chemicals are used, such as hydrogen peroxide or ozone or oxygen, to bleach the pulp and eliminate the lignin and the brown color that we know of the kraft pulp. And these steps are not used alone. Usually, we need to combine different steps with different chemicals in a good order, and we call that a bleaching sequence. And depending on the bleaching level that we want, we can combine different steps. So this selection is necessary to achieve an efficient bleaching. Yeah. So how do you say, on a complete kraft pulp, we can introduce the bleaching sequence directly at the end of the kraft cooking, where the wood chips are defibrillated and screened, and they are introduced into, for example, an oxygen delignification step that can be followed by hydrogen peroxide stage and so on. And at the end, we obtain what's it's called market pulp, that can be sell like a market pulp, or it can be also converted into paper with a conventional paper mill, and it can be also specialized and so on with some finishing steps. So an interesting and important steps to improve properties of this pulp is the refining. So here the refining, it's a mechanical treatment which is performed on fiber suspension, and it will increase the mechanical performance by modifying the physical and morphological fibers at the fiber level. Yeah. The principle is that depending for all type of refiner, the pulp is going into a small gap where we have shear forces, and these mechanical forces modify the fibers during only few milliseconds, and it will improve fibers properties such as mechanical ones or optical ones. Okay, next slide. Yeah, so different types of refiners. So at laboratory scale, we have the Valley Beater and the PFI refiner, that are two refiners that can be really useful to compare different pulps at a laboratory scale with a few grams of pulp treated, so quite easy to manage. And at industrial or pilot scale, we have the conical and refiner, or the disc refiner. But I think the most used is the disc refiner with a double disc refiner construction, and it is really efficient, and it really improves the mechanical properties of fibers. And yeah, next slide. Yeah, so the refining has some different effect at fiber structure. So we have usually three different effects, which is the cutting of the fibers. So the fiber length will decrease, the external fibrillation of the fiber that will create different links between the fibers, and the internal fibrillation that can also improve, for example, the absorbance property. So we have two images of a light microscope images of a pulp, one before refining, where we obviously see the fibers are like are just straight rods, and after refining, after super refining, the fibers have been decreased in length. We can see some few external fibrillation between the fibers, and some fibers have also some internal fibrillation. And yeah, two parameters that we can analyze, for example, during refining, are the fiber length, which will considerably decrease. For example, here from 800 to 300 after super refining, and the fine content, which represent the elements between 5 microns and 200 microns, that will considerably increase, and it will improve the bonding between the fibers. And the paper properties, yeah, will depend on refining power and time. If we want to improve properties, we can increase the refining, but at one point, if we increase too much refining, the fibers will be too short to have good mechanical properties. So we need to find the good points to have the wanted properties for the selected application. With this kind of pulp, several applications can be targeted. For example, with unbleached kraft pulp, we can target paper for carton box, for example, for e-commerce, or for kraft craft bags for fast food and so on, and in general, yeah, for food application. With a bleach craft pulp, usually, so we are targeting printing applications where we need to have a super bleach paper with a good smoothness and surface properties, but also tissue applications, which are also white and yeah, printing, and also art and decor application, for example, with a wallpaper. And I will introduce the next topic, which is the microfibrillated cellulose. So from these two different pulps, we can obtain two different microfibrillated cellulose products. So the one containing lignocellulosic, meaning just the craft pulp without bleaching, that we can find also in food application or in composite or in electronics one. And the bleach microfibrillated cellulose produced from bleached craft pulp is used, for example, also in a food application, but also in coating for improving or adding properties at the surface of a paper, and also in a thickener for food or for rheological things such as paint or so on. So yeah, regarding the microfibrillated cellulose, so we have different kind of materials. So the common materials is the cellulose nanomaterials. So it means it's a material composed of cellulose at nanoscale. And in this general family, we have nanocrystals, which are composed of cellulose, of crystalline cellulose that has a rice shape, like a straight rod on, for example, yeah, on these pictures. And on another side, the cellulose microfibrils that we call CNF, which are composed of elementary fibrils at nanoscale, and it's more like a spaghetti shape. So this is quite a good representation and common to see the difference between these materials. So how do we obtain these materials? So we start from pulp suspension that can be mechanically pretreated to decrease the fiber length. And then this pulp suspension, we can introduce that into an homogenization step with or without a pretreatment before. So here we can see an homogenizer, which is a device which will defibrillate the fibers by pushing the fibers into a small gap at really high pressure. It can go until up to 1,500 bars, or we can have this microfluidizer with a Z shape, which will also defibrillate the fibers in this Z shape. And on another side, we can produce cellulose nanocrystal by acid hydrolysis. And we can see on these two pictures really the difference in terms of morphology of these two nano products that have a good different properties. And I just added this slide to understand that from one raw materials, depending on the different steps to produce nanocellulose, starting from purification, meaning cooking and bleaching, and then we can introduce a mechanical pretreatment to improve then the production of nanocellulose. We can also introduce a biological with enzymatic hydrolysis, for example. And then finally, the mechanical treatment that can be from different natures, starting from homogenization, grinding, refining, extrusion, so on. And also some post-treatment to improve and or to add properties at this cellulose nanomaterials. So with all these different steps, we can obviously see that we can have many different kind of cellulose nanofibers with more than 50 types, for example. And just to conclude about this presentation, we wanted to highlight the Bio-LUSH process that we are working on with all our colleagues into the European projects. So we are starting from poplar wood residues that we convert into poplar wood chips. So the poplar wood residues are coming from plywood industry. And these poplar wood chips can have a mechanical pretreatment with the action of an enzyme to then improve the cooking. So the cooking we are working on, so we here at FCBA, we are working on craft cooking, which is a conventional cooking. And we are also developing a soft alkaline cooking, which is the heart of the project, where we will transform the biomass into pulp. This pulp can be bleached with a totally chlorine-free bleaching sequence that is developed also in the aim of the project. And but we can also pass from the pulp to the next step. And the next step here is an endoglucanase treatment that will target the glucose part of the cellulose, and it will improve the next step, which is the refining. So we are working here with a conventional low consistency refining of the pulp to produce at the end microfibrillated cellulose by different ways with Masuku or homogenizer. So it's grinding or homogenization. We are comparing also the two different processes. And finally, as explained previously, we are targeting different applications with, for example, with the lignocellulosic MFC, we are targeting electronics, composites, reinforcement in composites, yeah, and for example, improving also barrier properties for food application. And for the bleach MFC products, we are also targeting food application with barrier properties, but also coating and rheological applications too. And we thank you for your attention. And if you have any questions, please do not hesitate or contact us later if you want.
Thank you very much, Sandra, Arthur.
Thanks you.
That's very, very insightful. Thank you very much. And actually, it kicks up a little bit the theme for our next session that will be on the usage of the fibers for industrial users.
Yeah.
So Arthur ended up talking a little bit more on how we can just scale the usage of these fibers. So I would like to open now for questions for Sandra and for Arthur. Um, if anyone just wants to say something, please feel free or write it down on the chat. No, everybody is very is either very shy or Arthur and Sandra were very nice presenters and left no space for doubts, and everybody just is very well understood on what they wanted to say. So before we end and moving on, I would like to do something that we have been doing on our last sessions, which is I want to make our next session a participation. So I want everyone to help us build up this road on our sessions, because we want to address the topics that are really meaningful for people. So I invite you to go into Slido, either by scanning the QR code we are sharing now, or by following the link Mafalda just posted on our chat, and vote on between the different topics we suggest there. Which ones do you think would be more interesting for you to learn more about on our next session? So now we are entering summertime. So instead of moving on at our regular rhythm of the beginning of the month, instead of having this on August, we'll skip the August month because everybody will be mostly on vacation. So we'll resume on September 1st, the first Monday of the month once again, and I'll invite you to vote. Pay attention to our Fibs and social media on LinkedIn. Join in, follow us. We'll keep you posted. We'll keep you updated. And I would like I would like to see everyone that was here today to come and join us again in September when we resume these talks. So I see people are voting now. Okay, we are tied up on the innovations in industrial processing of green fibers and the overcoming the challenges of cost, supply chain, and scalability of this kind of businesses. Okay, Mafalda, I don't know if you can access how many people have voted yet. I would say 7.
7.
Yeah.
I would just like to say the same for the Bio-LUSH project. So if you want to know more, if you want to stay tuned about what we are doing, also follow our social media and website. And if you want to go back to this webinar and as a reminder of what our speakers talked today, this will also be published on the YouTube channel. So no worry.
Yeah, and we at FIPSEN and also our colleagues in Bio-LUSH will be sharing on our social media the links to the YouTube video. So if you want to share with some colleagues that didn't have the chance to be present here today and who you think might be relevant for them to learn a little bit more of what we spoke here today, feel free to share with them, invite them to follow FIPSEN and Bio-LUSH projects just on LinkedIn. And we'll be sure to keep you up posted with some more news, some new events, and it's the best way to keep up the rhythm to all that we are doing. So 9 people have voted now, so most people have already voted. So the most relevant topic for everyone will be the overcoming the challenges, which I think is always the doubt is how we can make this economically viable in terms of the cost, supply chain, and how to scale up. So let's try to find some interesting speakers to address this topic for September. And if no one else has any more questions for our speakers today, we'll end up the session, and I hope to see you all again back in September.
Thank you, Pedro.
Thank you very much, Arthur, Sandra. Percy, unfortunately, couldn't stay
Yeah.
until the end with us, but well, I'm sure everybody enjoyed this day.
Thank you.
Bye bye.
Thank you. Yeah.
Thank
Bye bye. See
you.
you.
See you in September. Bye bye.
Yeah. Bye. See you.
Bye bye.